Okay, today our new topic is vector space. Let's see what about the vector space. A vector space is a set of vectors for which the addition and the scalar multiplication are defined such that if u and v are vectors in the space and k is a scalar, then u plus v, the addition of two vectors, is in the space and the scalar multiplication with vector also in the space. So this is a general definition of a vector space. Let now I have taken here the three vectors u, v and w which belongs to v. V is actually a space, a set. Okay, here v means is denoted as set. Okay, one second. V is denoted here as set. So u and v and w, one second, u, v and w, this all vectors are belongs to set v. Okay, or in the space. Okay, so then we will say that v, this set, is vector space if it holds the total 10 properties. Okay, so what the property here, the scalar, we assume ab is belongs to a set of real number. So our number first one properties is the closure under the addition property. So if we add the two vectors is which belongs to a space or set v, for all u belongs to v and small v, the vector v also belongs to v. So as the vector u and v belongs to a set v, then we can say that u plus v also belongs to v. So adding the two vectors stays in the space also. Number two, the commutative law. So as the u and v is belongs to our space or set v, then u plus v equal to v plus u. So commutative law also hold. So order does not matter here. And number three, associative law. So in bracket u plus v plus w, which is equals to u plus in bracket v plus w, for all u v w is belongs to set v. Okay, if u v w are in the space, then the u plus v plus w, u plus v plus w, which is equal u plus in bracket u plus w. Okay, so grouping does not matter here. And now next, our the zero vector exists. So there exists a zero which is belongs to a set v such that vector v plus 0 is equal to vector v. So 0, as 0 is belongs to set v, or are in the space, 0 is in the space v, so is called a zero vector actually, and zero vector is denoted by theta. Okay, number 5, the additive inverse. For all the vector v, there exists a minus v such that v, vector v plus minus vector v, which is equals to 0. So that's mean every vector has an opposite. Okay, every vector has an opposite. And number 6 property is the closure property. Okay, closure property, closure property, closure under the scalar multiplication, closure under the scalar multiplication. So a times vector v, where a is a scalar, is also belongs to in space v. So multiplying by a number stays in also in space v. Okay, and number 7 is distributive over the vectors. So here a multiply with u plus v is give us au plus av. So scalar distribution over addition, this is called the scalar distribution over the addition, where uv belongs to in space, okay, v, or uv belongs to set v, and scalar a also belongs to field f. Okay, and the distributive over the scalar. So for the distributive of the scalars, we write here the a plus b. A plus b, what? A plus b is belongs to field A. AB is the scalar. Okay. And multiply with vector v give us AB plus VB. Okay. For all v, vector v is belongs to uh, the set of v. Set v. Okay. And associative property. Associative of scalars. So if we multiply A with in bracket b v, which equal to, we can write it ab times v. So multiplication order is does not matter here. So ab is same things. Ab is scalar, ab are scalar which belongs to fields f, and vector v also belongs to a space v. Okay. And 10 properties identity element. So identity elements 1 times v, which is equal to v. So if we multiply with identity element, okay, with the any vector, so it's give us the original vector. So for all the that vector is belongs to that space or that set. Okay. Okay, so now let's see uh, an example related to economics. So here consider an economy with the two goods. Here the x is quantity of rice and y is the quantity of wheat. And define V. This is a set. This set is represent the all possible production bundles. Now we will prove that V is a vector space. Okay, so let at the first let u equals to this x1 y1 element and vector v as the two component x2 y2 and w have the x3 y3, and uvw is belongs to set v. Okay, uvw is belongs to this set or this space. Okay, and ab scalar is belongs to set of real number. So our first exam is addition exam. So the closure property u plus v, just put the vector u and vector v and add them. We have this. Okay. As u v belongs to set v, so their addition also belong to set v. So closure property holds. And commutative property, we can write here u plus v. We can write x1 x2 as x2 plus x1 and y1 plus y2 as y2 plus y1, which is equal to v plus u. So commutative property as a whole. So here in economics sense, the closure property actually the combining the production. Okay, combining the production of u and v gives the another valid uh, production bundle here. And in case of the commutative property, commutative law, so the order of the combining the production does not matter here. Okay, so u plus v equal to v plus u. And for the associative property, we can write in bracket u plus v plus w, which is equal to u plus in bracket v plus w. So grouping of economic data is does not affect our total production. Okay, grouping of economic data is does not affect our total production, right? So associative property holds here also. And zero vector for 0 0, which is belongs to set v, and if we add xy plus 0 vector. Okay, this vector with 0 plus 0 vector is give us xy. Actually in economic sense, if I say that here 0 0 is represent the no production, right? So zero output in the economy. Here 0 sometime in economy happen the zero production or zero output. So this will be same here. Okay, so here the zero vector also holds an additive inverse, and for the additive inverse we can see here that it's give us result 0 and 0. So here the negative, this negative is denoted here the negative production, that is the loss or debt or reduction, which cancelling the output actually and give us a zero vector, right? And number v is scalar multiplication axiom. So Sixth property is closure. So under the multiplication axiom, there also has this closure property, distributive of vectors property. Okay. So number first is closure property. So a multiply with x y, this vector is give us ax and ay, which is also belongs to set v. Okay, that's mean the scaling the production, that's mean the scaling the production increase or decreases our output in our set v, right? So if a is any negative value, then our production is decreases here, and if our a is any positive value, then the production is increases, right? So the closure property also hold here, and the distributive over the vectors, we can write a in bracket u plus v, which is equal to au plus av, right? Right. So actually here the scaling the total production, this is u plus v is actually the total production, and multiply with scalar a, that's mean the scaling the total production is equal the scaling the scaling each economic data separately here. Okay, and distributive over the scalar. So here we can write a plus b times in bracket xy, which is give us ax plus by, ax plus by. So the combined investment effect here, which is equal to the sum of the individual effect. So distributive over scalars properties also hold here, and associative property, we know that a and bracket b times vector v, we can write it ab times v, right? Ab times v. So this, and identity property, one times the vector this, which result x y. Okay, which result x y. So identity property also hold here, and it indicate actually that no change in production when the scaling factor hour is 1. Okay, so as the all operation are satisfied, means the always produce a valid economic bundles. So thus the set v, this set v is a vector space, right? The all the 10 properties holds for the vector space. So we can say that our set v is a vector space. Okay, here xy is represent the bundles, different bundles, right? And xy is belongs to the set of real number here. So, and next is our subspace. So w is said to be a subspace of v if w is a subset of v, and w is a vector space in its own right, and that is it satisfies the all the axiom specified above for a vector space. So actually in simple, so this is a let let's suppose this is a space or a set v, and v, this set is satisfied the all the 10 axiom 10 properties of vector space. So we can say that v is a vector space, and here I have a w, right? Here I have w. So w will be subspace of v when it hold the two property. Number one, w is a subset of v, and number two, w is a vector space is in its own right, that is it also satisfies all the axiom of the vector space.